I will begin with a word of prayer. So we're down one, but she'll show up. Dear Father, we thank you again for this opportunity we have just to meet together and study math. And I just pray you give us understanding today and just guide my thoughts and help the students to understand them, Lord. In your name I pray. Amen. So what I thought I would do, in the interest of not spending this whole lecture on limits and continuity, stick with the projector, try to wrap up what I have to say about limits and continuity, and then put us away and I'll try to do differentiation on the board. Well, I foolishly assumed that there wouldn't be a bunch of hooligans running on the roof today. But anyway. Yeah, isn't it raining?
Yes.
Morons. Let's see here. Sorry to any of the Moors out there in the audience. It was very insensitive of me. But, sorry. I had European friends that, I told you guys this before, but they got first time I said morons to like some European students I knew, they're like, oh, that's very bad. I was like, they're like, it's racial. I'm like, not in this country. Like, it's really not. Mormons? No. I would stick with cultists, but anyway, let's hear. Okay, so we got open balls, we got closed balls. We talked about sort of the punchline last time. We got to if you have a component, if you have a function on norm linear spaces and you have component functions, if you know the limit of the component functions each exist, then you can put together the limit of the whole thing by just taking the appropriate linear combination of the limits of the component functions. And so this is what allows us to do, for example, I mean, ultimately, once we talk about differentiation, this theorem actually is why it makes sense to just define like derivatives of paths component-wise. Like the limit of a path is the vector of the limits of the components of the path is what that ends up meaning. Well, I'm not quite done here yet, but the converse direction turns out to be a little bit trickier. So let me get to that. First of all, one of the roadblocks in giving a really simple proof is this little tidbit. Certainly for nice bases, it's true that the magnitude of a component is less than or equal to the norm of a vector, right? Certainly for like the standard basis, the real and imaginary part of a complex number in magnitude is smaller than the magnitude of the complex number as a whole. Same for the Frobenius norm and like the magnitude of a particular entry of a matrix. It's true for all of our nice examples. But in principle, you could think about, here's a basis for R2, 1 epsilon, 1 0. Those are linearly independent. It gives you a basis. But if you look at this, x is equal to 1 comma epsilon minus 1 comma 0, well, that gives me 0 epsilon, right? So the norm, the Euclidean norm of x is just epsilon, if epsilon's positive. And yet the components are both 1 and minus 1. So the components both have magnitude 1. And it's quite clear that 1 doesn't have to be smaller than epsilon because we can make magnitude epsilon as small as we want. So like for generic bases, this just is not true, annoyingly so, right? So this is a special property that I want. For this special property that's true for certain nice bases. That's basically what's causing a technical sort of rift in my notes here. It's making me do some things that are a little bit technical here. But they're good for us to talk about also. There's something interesting that I need to say to address this issue. So it's still worthwhile to spend time on it in here. First of all, coordinate change. If we have two different bases for W, right, then we can calculate, there's a change of basis matrix Pij. So basically this defines the change of basis matrix. I can write W bar in terms of sum over Pij of Wj. And that's the change of basis matrix. It turns out, notice the flippity-floppity of the orders here. So this changes W to W bar. The same matrix changes bar to unbar. So it's inverse, like the appearance of P, it's see what I'm saying? This is usual thing. The matrix will change the basis opposite the way it changes the components. There's usually this sort of dual coordinate change for coordinates versus bases. We'll come back to that later in the course. So let me just not belabor it here. But basically what this lemma says is simply that if you have different bases, then the component functions of a vector valued function of normed linear spaces is related in the natural way, just like that. It's really nothing more than just a linear algebra result tacked onto functions, okay? It's nothing. So this argument I give here, if you remember me talking about coordinate change in linear, it's something I did, more or less. It's also something I'll get entirely confused about if I try to talk about in detail right now. I can tell you that. Given my current level of tiredness, I am going to go on. But when I wrote it, I was rested, so it should be okay. Now, if the limit of the, what? Come on. This is, seriously? There's an I missing here, f bar sub I, okay? Sub I is a component function with respect to the barred basis is equal to that for each one. Then you can build the limit of the function in terms of the change of basis matrix and the limits. So if I can calculate limits in one basis, I can assemble the total limit using the change of basis matrix if I want. I mean, I could also just straight up build it as linear combination of the basis, but this gives me a connection between limits calculated in one basis and another. All right, then three big ideas. The metric, and this we talked about a little bit already, the metric topology for a finite dimensional normed linear space is independent of the choice of norm, right? It doesn't matter whether we think about a circle, a taxicab, like a diamond or a box. Either way, our notion of openness is the same in finite dimensions. It turns out like that's not special to the plane. That can be proved in general. That's related to the Homer problem I gave you with the three norms. The thing missing is proving that there exists the M and the M to make it so, but that's a little bit more sophisticated. I have some links in the Homer problem to finish that thought, but it's a little bit beyond the course. So different norms generate the same topology, all right? The other thing is, and this is one of your Homer problems, is if you've got a function of normed linear spaces, then it's continuous if and only if the inverse image under F of each open set in W is open in V. So continuous function is one that the inverse image of open sets is open. This is equivalent to the epsilon delta definition. And it's actually not hard to prove that. It's just mostly definitions if you sort through it. It's really not that bad. It seems scarier than it is. It was very difficult with my problem statement being incorrect. Thank you, Cooper. Fixed it. Then here's the point 3. Since different choices of norm provide the same open sets, it follows that the calculation of a limit in a finite dimensional norm linear space is in fact independent of the choice of norm. So what that means is I can take my problem, I can pick the norm that I like, calculate the limit, and then I can use my change of basis. Well, then I can calculate my limit, and I know that that limit's going to be the same as it would be if I used a different norm for that finite dimensional space. This is very freeing because it means I can just construct a norm that got a nice property. So this is a way to construct, like if you give me a vector space, I can construct an inner product on it and hence a norm using this standard trick here. So like you give me a vector space, finite dimension with basis v1 through vn. I define an inner product, which is like a generalized dot product, by just saying the inner product of x, well basically the length of x is simply the square root of the sums of the squares of the components. This will define a norm on the vector space with basis beta, right? That doesn't have to match the norm which is given in the abstract, but it doesn't matter because if you calculate the limit with respect to this norm, it's going to be the same limit as if you calculate with the norm that's given in the example. We're starting at 420, but you didn't miss anything. Yeah. It just occurred to me he's not late, he's just following the schedule. Yeah. So, you know, you might worry, oh, what if there's a finite dimensional vector space out there that you can't put a norm on? Not a problem. Like, you can always invent this stupid norm. with respect to a basis, which basically just says, I'm going to do Cartesian Euclidean norm with respect to the coordinate system given by that arbitrary basis. That may be completely divorced from the actual geometry of the problem, but it's still something you can use to calculate limits. Now, this is all I needed. Then basically that's all just so that I can argue that I take the norm I'm given, I say forget about it, pick a nice norm where I've used that, the norm built from inner product, because the norm induced from inner product has that property that the magnitude of any component is less than the magnitude of the vector. That estimate I need in order to make this argument. That's basically the reason for all of this. So here it is. Suppose that the limit of f of x, and the idea here, we've already proved this direction. This direction I proved at the end of last class. Given that all the component functions limits exist, the limit of the whole function exists, it's just the sum of the limits with the basis vectors. Now I'm trying to go the other way. If the total limit exists, then each of the component functions has a limit which exists in the natural way. This altogether is what I call the vector limit theorem. It says when you're dealing with a norm linear space, a function on norm linear spaces, we can divide and conquer. We can understand the limit of a vector valued function in terms of the limits of each of the component functions strung together. All right? So here's the proof. I assume the limit exists. I construct my silly inner product that forces the orthonormality of that given basis. And I extend bilinearly. Fine, I'm just defining it. Extend bilinearly. Let, here's my norm, my made-up funny norm. Not necessarily the norm which is given for W, all right? It's my ad hoc norm for the purpose of this proof. So in this construction, it basically forces the length of the basis to be 1 with this notion of norm. And it also gives us this estimate that the magnitude of the ith component is less than or equal to the length of y for any vector in W. And so I get this estimate, which is all I'm after, really. The ith component, the absolute value of the ith component is equal to, see this? Well, this is 1, right? Then by properties of norm, I can bring in this positive quantity inside, like so, right? I guess at this point, well, it's either plus or minus, right? But I can eat the plus or minus into the norm. I mean, the signs don't matter. So there's that. And then, but this is the ith component of that vector. But then the thing is, if this limit is given, I control this. If x is within delta units of the limit point, I can make this smaller than epsilon. Consequently, I can make that smaller than epsilon. Consequently, the limit of the ith component function exists and is b sub I. Now that's all done with respect to this ad hoc norm I invented to work with respect to the beta basis, but it doesn't matter because the limit is the same no matter which norm you use. So the fact that this limit exists in this Euclidean norm I invented by the 1, 2, 3 comment I made on the previous page, the same limit holds the same limit holds with respect to the norm which is given in W. It's kind of sneaky. And then the converse direction actually follows from the theorem, the limit laws we proved last time, but I give a standalone argument here which is worth looking at for just a minute. So let's do that. So suppose that you are given that each component function limits to b sub j. Choose epsilon greater than 0 such that if you're within delta sub j units, we get that the norm of f sub j minus b sub, this is actually, I don't really need norm here. I could say what? Absolute value. These are real numbers. So that's not necessary. And then this is for reasons that will become clear. Okay. M is the dimension of W. And then you just let delta be the minimum of all these guys. And look at this. So this is equal to that triangle inequality, m-fold triangle inequality. use my estimate, less than that. The WJ's cancel, and then you get epsilon over m, sum j equal 1 to m, but that's epsilon, so woohoo.
So that is not, the norm is invaded.
Say again?
That norm is not necessary Euclidean norm.
Yeah, the second part doesn't, this direction I don't need to do anything, any kind of funny norm changing stuff. And maybe there's a way to do the first part without doing norm changing if I was a more skilled analyst. It wouldn't be hard. All right, I will dispense with proofs. That's the only one I wanted to tell you. The rest I'm just going to tell you the results, okay? There is a sort of chain rule for limits. I mean, it's a composite limit rule. If you have a continuous map, then you can bring limits inside the composition. So like the limit of f of g of x is f of the limit of g of x. This is super nice, and the proof is actually pretty easy. You should be able, after you've done the homework, I bet you can understand that proof in like 3 minutes reading. It's not that bad. Then you can prove, and this would actually require considerably more effort on my part in here if I was to really do it. You can prove that the sum and the product functions are continuous on R2, from R2 to R. This one's pretty easy to prove it's continuous. This one's a bear for me. Although Min made an argument using algebraic and geometric mean inequalities that considerably simplified my work, and I never put it into my notes. My previous version of my notes has a very clunky proof that that's continuous. It is. But the cool thing is once you know these are continuous and you know that the composite of continuous things is continuous, then you can use these, and well, one other thing. By the way, if you have real valued functions, the product of real valued functions, so I'm supposing I have a function from a normed linear space to the real numbers, so you can define the product of them. Well, then the limit of the product is the product of the limits, if they exist. So like limit of f times, this is just the product of real numbers. It's the product of the limits. We also have this result. And it's like, well, how do you have that result? You just rewrite this as p composed with f and g, but if the product function is continuous, we can just use the composite limit thing to pull the limit inside, and then you use the vector limit thing to say that the limit of f comma g is the limit of f comma the limit g, right? So this is the continuity result I just had on the previous page. This is that theorem that I worked harder to prove, that the limit of a vector is the vector of the limits, provided they exist. And then, bam, that's the result. So you start building up enough of this, you can stop doing epsilons and deltas and just use properties, yeah? That's the dream. No epsilons, no deltas, just algebra. Well, that's my dream. It may not be. Certainly that is not the dream of most professors who teach real analysis. They like to stay in the epsilons and deltas, and some of them more than others. But this is a super useful result. If we have a normed linear space with basis v1 through vn, you can define the coordinate function x of I as follows. So if I have a1 v1 da a and vn, then x sub I of a is equal to a sub I. All right, this is the I coordinate function. It takes in a vector, it spits out a number, right? Then the coordinate map is actually the Cartesian product of these functions. It's like, what this means is that if I take phi beta acting on a, what is it? It's x1 of a, comma x2 of a, comma xn of a. So I'm using this notation for like the Cartesian product of functions. I'm thinking of x1 and through xn as functions here. But the point is the coordinate map is just this vector of coordinate functions. And by the way, each coordinate function is continuous. So the proof, I should have made a homework. I think I forgot to make it a homework. Did I make it a homework? I think this is a pretty easy homework, but it's not hard to prove that the coordinate functions are continuous, right? So then what? Then you could look at multinomials. like polynomials or polynomials in several variables. And they're built from what? From sums of products of coordinate functions. Things like this, I'll call a multinomial. And those are going to be continuous. Right? If I have a multinomial of the coordinates of a normed linear space, it's going to be a continuous function because it's the sum of products of continuous real valued things, which is again continuous, even in this general context. So here's what I'm really after. The determinant is a multinomial of the coordinates of a matrix. It's a sum of products of entries of the matrix. The entries of the matrix are the coordinates of the matrix. And so the determinant is a continuous function from Rn by n to R. Right? So, example. Oh, I guess I should just, I made my bed. I have to lie in it now. I mean, I will start writing when we get to the next chapter. I must behave. So this example is a beautiful application of all this. General linear group. What is it? It is the set of invertible matrices over the reals. N by n invertible matrices. We can argue that this is an open subset of matrices, meaning that if you look at the Frobenius norm, you pick any point, any set of invertible matrices, any particular invertible matrices, there is a neighborhood around that point full of invertible matrices. Right? In other words, every point of every invertible matrix is interior to the set of all invertible matrices. You can't get to an invertible matrix, take an open neighborhood around it, and somehow get a bunch of singular matrices in your neighborhood. Unless you're, well, I mean, fine. If your neighborhood's too big, I guess you could do that. But to see that, you just look at this, the GLNR, what is it? It's the inverse image of the non-zero real numbers, which are the union of the open rays to and from plus or minus infinity from 0. This is the union of open sets, which is open again. So GLNR is the inverse image of an open set. So it's open, using your homework. Now, think about proving that directly from epsilon deltas. Pick a particular matrix. How would you construct an epsilon? You know, how would you, for a given epsilon, how would you construct a delta such that, you know, you're within, I don't know. How would you construct an open neighborhood of a matrix? And I don't know. I've never tried to do it directly. This is such an easy argument that why would you? Maybe you're a numerical methods person and it matters, right? I don't know. Details. Let T be a linear transformation. Then T of x has component functions which are formed from first order multinomials in the coordinates, right? Think about a linear transformation. What's its formula? It's built from linear combinations of the coordinates, right? Those are continuous. So linear transformations are continuous. I mean, I gave this from Rn to Rm, but you can see that that would easily be true for like for a linear function from any norm linear space to another norm linear space. Finite dimensional, again, funny stuff happens in infinite dimensions. There's a squeeze theorem for real valued functions from a norm linear space. The proof is just as technical as it is in Calculus 1. That is my Calculus 1 proof, replacing absolute values with norms. Hooray. We actually need that squeeze theorem for examples I'm doing later today, so I mention it, okay? Sequential analysis is, so I just say a word or two here. I don't really do too much with sequences in here, but I give you a homework problem, so I should at least talk to you about it, right? So you guys remember what the definition for a sequence was? It's a function from the natural numbers to whatever you're looking at, right? So you can think of it as a list of vectors. And then we can talk about what does it mean for the limit as n goes to infinity of a sub n to be equal to L, right? That means, what does it mean? It means that if you go far enough out in the sequence, you can make values of the sequence, vectors in the sequence, arbitrarily close to your limiting vector, right? So just saying that the sequence gets closer and closer and closer and closer and closer to that L if you go far enough out, right? And this is the technical jargon to make that happen. For each epsilon greater than 0, there has to exist some number such that such that the distance between the nth term in the sequence and the limit vector is less than epsilon for all n that are beyond this m. In that case, we say it's a convergent sequence. That's, again, the same definition I gave in Calculus 2 if you took it with me, except instead of having absolute value, we do what? Norm, right? But otherwise, same definition. Cauchy sequence. A Cauchy sequence is one for which, if you go far enough out in it, if you take the difference of any two terms in the sequence, then you can make it smaller than epsilon. Now, these don't have to be successive terms. They just have to be terms past some point. There has to be some point past which you can get for each epsilon such that it, makes it small. So Cauchy sequences are ones that kind of get closer and closer together if you get far enough out. All right. Now, a good example of a Cauchy sequence would be something like this: 1 minus 1/2 plus 1/3 minus 1/4 plus ... The sequence of partial sums here is a Cauchy sequence, because if you draw a picture, right, you might need to, if you draw a picture, this is S1, right? The second partial sum is here, the third partial sum is here, the fourth partial sum is there, and they just keep tick 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 tick, right? And so if you pick m far enough out, the difference between any Sm and Sn can be as small as you like. So the partial sums in this series are Cauchy, right? Also, this is an element of the rational numbers, right? No matter how far you go, this is dangerous. Sorry, I shouldn't say that. What I should say is that S sub n is an element of the rational numbers for all n. But what is the limit of this sequence? What's that? Yeah, it's log 2, right? So in Calculus 2, I'll show that. So this is the alternating harmonic series. It converges to log 2. Is log 2 a rational number? It is not, no. So here we have a sequence, a Cauchy sequence of rational numbers, right, which converges to an irrational number. This demonstrates that the rational numbers are not complete. A complete space is one for which every Cauchy sequence converges to a point within the space. So real numbers are complete because if you have any Cauchy sequence of real numbers, it will converge to a real number. So Cauchy implies convergent for real numbers. And in fact, this defines a complete space. If you have a normed linear space, which is also complete, all right, then it's called a Banach space. A Banach space is a complete normed linear space. Now, I'm getting dangerously close to teaching real analysis right now. So let me back away from it. I'm going to back away from it. It is a very non-trivial matter to explain in detail why the real numbers are complete. That question strikes at the heart of the construction of real numbers. All right. For your information, you can take an incomplete space And you can adjoin all limit points of Cauchy sequence. It's called finding the completion of the space. There's actually a method to find a complete space from an incomplete space. That's like a well-defined mathematical procedure. There are different ways to complete the rational numbers. The one way is to get real numbers. With respect to a different concept of norm, you get what are called p-adics. If you want to know about p-adics, you should talk to Dr. Smith. I know nothing. So, I mean, I know just enough to be dangerous, but to show R2, if we know R is complete, showing R2 is complete, that's an easy thing. So what we do is suppose you've got a Cauchy sequence of vectors, all right? In other words, assume that there exists some m, or I guess to use n, such that you've got m and n beyond n without loss of generality. Assume that m is before n. Then that implies that the distance between the sequence of vectors in the plane is less than epsilon, all right? What I want to do is I want to show that that implies that this sequence converges. All right? So this is, well, that's just a formula. I mean, that's the definition of the stupid Euclidean norm, isn't it? And it's this thing I've been struggling with today, that the magnitude of the x components, right, is the magnitude of the difference of the x components is less than what? Oh no. Oh. Oh. Son of a gun. No. Well, there'll be a 5-minute recess. I'm just kidding. My computer reboots a little bit faster than that, but you know, I need to buy a new battery. It's gotten so it gets to like 40% and then it just turns off. So it's like, that's not really 40%. You tricky computer, you. Let's see here.
Are you a file called haha on your desktop?
Why not?
Let's not look too hard at my desktop. Let's see here. There's any number of things that could get me fired there. Let's see here. Well, that was kind of a nice break, wasn't it? All right.
Hey, Dr.
Yeah.
So, you said real analysis, Cauchy and Cauchy. Is there
Yeah.
a similar analysis here, or is it just not the case?
Cauchy implies convergent in a complete space.
In a complete space. That's the
Yeah. In fact, all of our examples are complete spaces, so. But, yes. Anyway, let me try to wrap this up so we get the differentiation. Okay, so the magnitude of a component is smaller than the length of the vector as a whole, right? And so I can make this smaller than epsilon. There exists an integer such that far enough out, right? I can make this smaller than epsilon, but consequently, I can make that smaller than epsilon, which shows that the difference between xm and xn can be made arbitrarily small for m and n sufficiently large, which shows that this is a Cauchy sequence of real numbers. But I know that the reals are complete, so that means that this xn converges to something, let's say x. A very similar argument, I can say ym minus yn is less than this. So yn is a Cauchy sequence of real numbers, consequently converges to y. And then I just argue that, in fact, I can propose that xn, yn converges to xy. And that's going to be, I mean, I actually give a limiting, I give an epsilon delta, I mean, I give an epsilon argument down here, but I mean, we could get that immediately from the vector limit theorem, right? The limit of xn is x, the limit of yn is y. So the limit of the vector is the vector of the limits, done. I'm really reproving the vector limit theorem here in the context of this particular argument, which is well, wait a minute. Why is it necessary? It's exactly the different kind of limit. It's just because I call both limits doesn't mean they're the same thing, does it? This is a sequential limit. So logically, this is needed. Sorry, I get carried away sometimes. But anyway, you just pick epsilon greater than 0, choose n sub x such that I get that, choose n sub y such that I get that. Why can I do this and why can I do that? It's because the limit of x sub n equals x and the limit of y sub n equals y. So I get to control how far yn is from y and how far xn is from x for sufficiently large integers. And then I just let n be the max of that, so I get my cake and eat it too. And then, you know, this is equal to that, which is less than or equal to that, but that is less than epsilon. So that shows that I can make this arbitrarily close to that for m and n, I mean for n sufficiently large, which says that the limit exists. And so that's an arbitrary Cauchy sequence. I just showed it converges. That proves that R2 is complete. Your homework problem is the same silly thing, except I think I gave it to you for matrices, right? So instead of doing it for x and y, you need to basically make the argument for aij. I'm not suggesting you be like, a11 is blah, 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 and then a12 is blah, 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 and then a13 is blah, 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 and then a21 is blah, 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 and no. You should argue for aij. Do I and j arbitrary, and then you'll get, you know, I mean, you can prove that the sequence aij of n is Cauchy, given that the matrix A of n is Cauchy. So, what's that? I don't think you need to do anything fancy with the norm because the Frobenius norm already has this wonderful property. Because the Frobenius norm is induced from an inner product, it's induced from an inner product in such a way that the matrix units are orthonormal. So, and finally, just so you don't think it's uninteresting, so you should appreciate this, Travis, because I'm actually doing something useful now, right?
So all of the other stuff isn't useful?
I don't know. I mean, it's just kind of like, it's kind of like integrity, you know?
I'm liking
It's useful, but it's sort of its absence, which is most obvious of its use. I mean, I don't know. Okay, so here, this matrix exponential, how do we know it converges? So we can look at the sequence of partial sums for the matrix exponential, and I can show with this little calculation that the norm of SM, so the nth partial sum of the matrix exponential. So if I look at the norm of the difference, I get this. Now, for the matrix norm has this wonderful property that the norm of a product of two matrices is less than or equal to the product of the norms. That actually means that matrices form what's called a Banach algebra because they're complete and they satisfy that quality, that inequality there. But anyway, my point is Sn is the nth partial sum of this thing. I mean, this is actually the nth partial sum of the stink. I should just have e to the a here, right? I mean, this would be the sum k equals 0 to infinity of it's this. This with k equals 0 to infinity would be that, right? Sorry about that. The point is that exists because calculus 2, it's an exponential of a norm, so it converges. And consequently, that allows me to show that this can be made arbitrarily small by the squeeze theorem, which shows that the nth partial sum for the matrix exponential is Cauchy. But by your homework problem, matrices are complete, so that Cauchy sequence must converge, which says that the infinite sum defining the matrix exponential exists for arbitrary matrix. And that is a very useful proposition because you know what you can do with the matrix. I mean, what can't you do with the matrix exponential, right? Now, in linear algebra, we have a rather different argument in terms of the Jordan form. You can calculate the real Jordan form for any matrix, and so you can calculate the matrix exponential for the Jordan form. There's a straightforward formula for that. And by consequence of this nice identity that, you know, e to the PAP inverse is P e to the AP inverse, the fact that you know this allows you to calculate that. This is a completely algebraic argument that supports the existence of the matrix exponential. Mostly algebraic. There's still analysis in showing that this converges to the nice formula, but yeah. Use the what?
Root test.
Root test. Root test.
Yeah, in the square root, square is the square root. Nth root of the n term will converge to something that less than 1. Because I think that's
Root test on what, though? I mean, it's a series of matrices.
use the norm.
The norm.
Norm each element greater than the absolute value.
That might work. I mean, I think there are other ways. There's a paper that has like 19 different ways to calculate the matrix exponential. So there's so much that's known about it. But anyway, let me put this away. Finally. Come on. Sit on. Thank you. All right, finally. So here's the definition. Let V and W be normed linear spaces, all right? And suppose that U is open. And F is a mapping from U to W, all right? Not necessarily linear. Then F is differentiable at A in U if and only if there exists L from V to W linear such that the following limit holds. The limit as h goes to 0 of f of a plus h minus f of a minus L of h divided by the norm of h equals to 0. So if this all happens, in this case, we write L of h is equal to d f sub a of h. So we say df sub A is a linear mapping from V to W, all right, is the differential of f at A. So comment, if V equals to R n and W equals to R m, then, dFA would be a mapping from Rn to Rm, right? Linear. And that means from linear algebra that we can say what? That's a linear transformation, so we can do what? We could say dFA of H is equal to the matrix of dFA times H. Okay, in that special context, we could rewrite the differential without a lot of further baggage as a matrix multiplication. Now, a typical notation, for this notation is seen in Edwards. He'll just write f prime of A for that. Now, I'm not using Edwards with you guys this semester, but I can't help but talk about him sometimes. If you ever want to look at Edwards, I got a copy in my office. I'm not hoping you read it or anything. I just, Anyway, so that's just a notation he uses for that. And this has a name. Also popular, we sometimes write J sub f of A for f prime of A. That would be an element of R m by n. It's the what? Right, the Jacobian matrix. Now, let's just talk about this definition. Like, what is it saying? By the way, some people will put a norm upstairs too, like the norm with respect to W upstairs. But I just put the norm with respect to V downstairs. It suffices. I prefer this definition. What it's saying is like the difference is saying, intuitively, what's the intuition here? Basically, we're saying that f of A plus H, right, minus f of A is approximately equal to, dFA of H, right? So this differential is giving us a good approximation to the change in the function, really the change in the map at that point. So do you guys have any questions as we're doing this? Like, what might you try otherwise? Like, I think everybody, without thinking, maybe you'd try, you might be tempted to write this, right? Why don't we just write this? Okay. What would the problem be with writing that? Not invertible. What thing here is, this is division by a vector is no allowed, right? Yeah, that's the problem. We can't divide. So we have to divide by the norm of the vector because that still makes good sense, right? So that's a lot of it. Now let's take a second to try to connect this. Let's see, how does this connect to calculus 1, right? So do you think, now I will sometimes, I said differentiable, but to be more precise, I sometimes say Fréchet differentiable because this is Fréchet's notion of differentiability. So let's look at example 1. What if we have a function from U, a subset of the reals, to the reals, right? And we have that the limit as h goes to 0 of f of a plus h minus f of a minus df a of h divided by, well, it'd be absolute value of h here, wouldn't it? Equals to 0. Did I post Zorich in course content for you guys yet? Did I post it yet? I don't think I did. I should remember to, not that it entirely matters to you that much, but, oh man. I was about to print my notes earlier today, and then somebody came and asked me about something and made me completely forget. Fortunately, I still have this one. Okay, so how to deal with this? So I give some arguments in the notes, and I'm not going to go through them, but it's fairly easy to argue that you can actually erase the absolute values here. Because if you look at the left and the right limits, they both have to exist and be equal to 0. And so you can pull out the minus from the absolute value. You, in fact, get the unadorned quotient equal to 0 in this case. And that makes sense because we're talking about real h, right? And so then what? Well, I always struggle with this bit. All right, fine. So we can simplify this a little bit. What is this? This is limit as h goes to 0 of f of a plus h minus f of a over h, right? Minus df a of h over h. Right. Now, let's focus on the right-hand term there. Oh, right, dfa is linear. What's that mean? dfa of h has to equal to m times h, right? Because we're talking about a linear transformation from R to R, which is just multiplication by a number, right? 1 by 1 matrix. So the limit dfa of h over h equals mh over h, which is equal to m, which of course goes to, well, not equal to m, but it goes to m as h goes to 0, right? So therefore, the limit as h goes to 0 of dfa of h over h is in fact equal to m. In other words, the limit of that piece exists, right? But there's a theorem from Calculus 1 that says if you have the limit of a difference equal to 0, right? And one of the things making up the difference exists, then guess what? This implies that the limit of the other piece is what? It has to also exist, and it has to be what? It has to be equal to m, right? So, lo and behold, we have just figured out what the how the differential is related to the ordinary derivative of calculus 1. How is it related? dfa of h is equal to mh, right? But this, by definition, is f prime of a, right? Difference quotient, calc 1, like week 2, right? So we got f prime of a times h. Which is why this notation in Edwards is, it's kind of okay. Sneaky, because his f prime of a is a matrix. But okay. So this is the natural relation between the differential and the derivative. And I mean, it's, if you start using dx for h instead, you start getting really cool looking formulas like df dx at a times dx. Yeah. But anyway, more on these sorts of things later. Okay, so let's actually do some examples. Start out with a really easy one. I don't think this is that easy. It's like sort of, for most students, reminding you of your least favorite part of Calculus 1. But I don't know. Maybe not you guys, but example 2. What if t from v to w is linear? Linear transformation. Is it differentiable? I propose that dt sub a of h should just be equal to t of h. In other words, I'm saying that dta should just be equal to t for all a and b. I'm proposing that. What do I need to do in order to prove that, in fact, this is differentiable at a? Number one, I need to find a differential, which is linear. Is this linear? I just said t was linear, so yeah. Now what do I have to do? I have to show that it satisfies the Frechet quotient, right? So let's do that. What's the limit as h goes to 0 of t of a plus h minus t of a minus dt a of h? Well, divided by, of course, norm h.
So when linear, we get t of a plus t of h minus t of a minus t of h.
Also known as the limit as h goes to 0. So much writing for so little thinking. The numerator is identically 0, right? So this limit is there you have it. A linear function on a norm linear space is differentiable, and its differential is just the map again. So the best linear approximation to the change in a linear transformation is the linear transformation itself. Not terribly surprising, but good. All right? Application of this. What's the derivative of the identity map? Right? So if I differentiate the identity map from v to v, I get the identity map again as an application of this. Right? Let me just propose it, not work out the details, but what would happen, what if I had t of x equal to a constant? Where t is again a mapping from v to w. Let me not do t, let's say f there. Constant function. What's its differential? The derivative of a constant should be 0, yes. In fact, yes. So dfa of h just equal to 0. So the 0 transformation will be the differential of that. Constant function's differentiable with the differential being 0.